and I will close. Okay, I will close it. I don't like this. Just a moment. Okay, let's start. So I'm Anatoly. I'm a chemist, doctor of chemistry, and been working a long time in academy, published about 100 scientific books, scientific papers, and one book about chemistry and technology of tantalum and niobium. I've been working as a private consultant to mainly to Vishay in Israel, Vishay in the United States, and very interesting chemistry. And about 20 years ago, I started working Intel, also very interesting chemistry. So chemistry is very interesting things. You know what I wonder that chemistry is the same, salaries are different. So 3 years ago, I retired from Intel and started to teach students in Ben Gurion University and consult company in United States and another company uh, in Africa. And I I'm co-founder of PRIZ Guru. We develop a platform for innovation and for problem solving. So let's return to the to Moore's law and material evolution. In 1943, a chairman of IBM published, I think there is a world market for maybe 5 computers. It was not bad, 5 computers a year. In 1949, it was published very optimistic prediction. Computers in the future may weigh no more than 1.5 tons. Where is this optimistic statement come from? Very easy. In 1947 was invented transistor, and companies started to produce transistor, and transistors started to replace vacuum tubes, electronic tubes. But no one was thinking about that in 10 years, I see microchip will appear, and this will really allow to produce a computer less than 1.5 tons. Intel is a leader of microchips. Started with this is very old chip. I'm not sure it's a CPU. It may be memory. This CPU was produced in the 74. This is more or less today's processor. They are similar because they have transistors inside, and the difference, they have very different number of transistors. What transistor is in semiconductor and microchip is a silicon wafer. There is a source, drain, and gate. Gate is a piece of metal or silicon which is sitting on the insulator, and if we apply plus the current will begin between source and drain. How to make this transistor faster? Very, very easy. We should just need to make it smaller. We just need to reduce distance between source and drain. And what's happened? We reduce distance, we reduce resistance between source and drain, we reduce size of the transistor, and we can insert much more transistors into the device, and we can use additional applications and so on. So very, very good. Gordon Moore started to analyze situation with Intel, and in 1965 he found that number of elements, components, transistors in the chip moves linearly in these coordinates. Here made his calculation after 10 years and found that the same. You know, it was incredible time. Very top managers were able to make statistical analysis. And what he said, you know what? This will be the law of evolution. Moore's law says number of transistors on a chip doubles every 24 months. Great. What's happened now? Now we live on this, according to this law, for more than 50 years. And have a look, in 17th, we had 1,000 transistors on a chip, and the current chips contains up to 10 billion transistors. Fantastic. So if you think this law impacted only microelectronics, it's wrong. It's completely wrong. First of all, it impacts the programming. I'm not very big professional in programming. I found a good article, and there are some parameters of programs, and you see complexity, lines of code, comments, and you can see Moore's law. Very interesting. Processors with a more and more amount of transistors and more applications requested more passive components. For instance, more tantalum capacitors. Tantalum capacitor can be done very small and with high capacitance, but we need very fine powder. So actually what's happened, that Moore's law forced power metallurgy, forced to develop very fine powders of tantalum to be used for making of tantalum capacitors. The surface of this powder, the parameter of this powder is CV, capacitance multiplied by voltage. It's charge of the powder, and you see how it increases. Guys, it's Moore's law. Not only capacitors, we also need resistors. And you see what's happened with the time, with the global market of resistors. And of course, resistors becomes very, very small. And people should create new technologies and new processes and new materials. Resistors become smaller and the market increased dramatically. Actually, what was done by Gordon Moore, He said, drive innovation every 2 years. Every 2 years, you need to implement innovation. This is actually what he said. And maybe in 70s, 80s was good enough to have 2 years to design and develop next generation, next device. For today's device, it's not enough. You should start 6, 5, maybe 7 years before. And in this case, you should think about materials that doesn't exist so far, and think about the processes that are not developed so far. Very interesting. This slide explains what node technology is. A lot of people use these numbers for technology. I just want to explain. Node technology, this is a smallest size, the size of gate, actually the distance between source and drain. And just to let you feel what we are talking about, in 2008, 45 nanometers, gate was 45 nanometers. We had 3.3 million transistors per square millimeters. Per square millimeter. And in 2018, 10 nanometers node technology already contains 100 million transistors per square millimeter. Fantastic, just fantastic. A few words about manufacturing of chips. Chips are made on the wafer. This is a testy wafer. This one silicon wafer, typical size 300 millimeters, and on the wafer printed about number of maybe 600, 800 dies, and when after production, this wafer is cut, and each die, it looks like this, separated and sent to, after testing, sent to the package. In order to make it, we need to grow silicon single crystal. We grow it with a Czochralski method. Very, very nice method. I use it for growing single crystals of lithium tantalite, lithium niobate. The principle is the same. You have melt, you have small single crystal, and this crystal rotates very slowly and moves. And actually, the single crystal, the seed pulls single crystal from the melt. Czochralski machine also has a name, pulling machine. So this is the size of single crystals, very unique process. And after that, we cut these wafers. We treat, we wash the surfaces, we polish it, we edge these, and in the end, what we have silicon wafer, 750 micron thickness, which is like 7, 8 pages paper, and this is single crystal. It's oriented, and on the surface, the phase 100. What's interesting, we spent so much money for this wafer, and we never touch this wafer during the process because this surface is not good. It's polished, etched, but it's not good for small transistors. Therefore, on the surface of wafer, a silicon is deposited by epitaxial. By epitaxial, it means it received the same crystallographic directions as their support. So we create silicon wafer and we never touch it. Interesting. So transistor, as we said, it's silicon, source, drain, we have gate, and gate is a piece of metal or maybe a piece of silicon sitting on the gate oxide. And this is a capacitor. When we apply plus on the gate, this capacitor should keep a charge. And we make this transistor smaller, 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 smaller. And what's happened with the capacitance, A is reduced. And in order to compensate it and keep capacitance of the same level, we reduce the thickness of gate oxide. And what's happened with their certain time, we have so thin gate oxide that it becomes so leaky, and which is not a problem for transistor performance, but it's a problem for battery. We just kill the battery very fast. What should we do? We should change dielectric permittivity. And we replace silicon oxide, which is typically was used as gate oxide, silicon oxide, K equal 4. Or we use gadolinium oxide. Actually, any oxide I read in articles that already niobium oxide and tantalum oxide exist. And actually, any rare refractory metal oxide is okay because it has relatively high dielectric permittivity, 25 up to 30, even 40, because of crystallographic structure. Hafnium in this case is located within the octahedral, and it is a little bit free within the octahedral. Therefore, it is shifted a little bit from the center and creates dipole. Dipole increases dielectric permittivity. We continue to make transistors smaller, 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 and source and drain becomes more closely one to another. And we get to the situation that there is no enough electrons between source and drain. This is trivial explanation. What do? We remove silicon from source, from drain, and we fill it with a mixture of silicon and germanium. Silicon germanium, they are like brothers, they're from the same group, but germanium is more metallic and can contribute much more electrons. So we etch this and we place here mixture of silicon germanium epitaxially. It means this deposited material got the same crystal structure as their epitaxial silicon. This is cross-section, typical cross-section. So we continue to reduce distance between source and drain, and we got to the situation that surface is very, very small, and we need to do something. And we moved from planar transistor to tri-gate transistor. You see, it was planar and source and drain like here, and we moved to tri-gates and transistor. Now, source and drain should be created on this fin, and this is only for to increase the surface to be able to manage better the performance of the transistor. Very complicated, very complicated way. Not only transistor, when we reduce the size of transistor, we also impact interconnection. You know, we need to connect transistors. We need to connect the source and drain and base from different transistors with the wires, and all this system calls interconnection system, and it consists of dielectric. It's typically CO2 silica or modified silica and metal lines. This is a cross-section of 22 nanometers technology. Transistors we cannot see here, but all these are interconnection layers. We have lines, it's wires, and vias. These are connections between different layers. Not only what's happened when we reduce the size of the transistor, we make all wires, all metal lines to be smaller and smaller, and we increase resistivity. More than that, they become closer one to another, and we increase capacitance that are rising between metal structures, metal lines. So we increase R and we increase C. We increase resistivity and we increase capacitance. If we multiply ohm by farad, we will get second time. It calls RC delay, and RC delay is the key parameter of microelectronics. Why it's important? When we connect different transistors with a wire, it's not only wire, it's wire containing resistors and capacitors. And as a result, it impacts our output signal. If input signal is looks like this, output signal will be destroyed with RC delay because it's not ohmic connection. This is because of impedance. How RC delay limits and destroy our life, works against Moore's law. Very easy. This graph is, here is delay in nanosecond, delay. And here is transistor gate size, pitch, gate size. When we shrink transistor, make it smaller, smaller, we move into that direction. So transistor delay, what's happened, it goes down. It goes down, and because transistor becomes more and more, it becomes faster. RC delay increases because R and capacitance, resistance and capacitance increase. And when RC delay is below transistor delay, no problem. We can continue to make shrink, to make transistors smaller and smaller. But when they meet, there is a problem. We can continue to make transistors smaller, but delay totally will be increased. And actually, RC delay will manage the speed of the device, and part of energy will be converted into heat. And heat is always connected, is related to, occurs on the interconnection. So this is the limit. In order to continue to shrink transistors, we should reduce RC delay. For instance, we reduced it somehow and we got here. So we get additional budget for shrinkage, for making transistors smaller, and we, we get additional budget to follow Moore's law. How to reduce RC delay? We need to reduce R and C. Let's start with R. About 25, 30 years ago, something like this, we switched from aluminum to copper. About 25, 30 years ago, all metal lines were built from aluminum. And one day, people decided that we should get switched to copper because copper is much more conductive. I show here electric conductivity versus temperature in order not to show you just one point, these curves. And we win 60% due to replacement of aluminum for copper. What are advantages? A lot of advantages. First, high electrical conductivity, high thermal conductivity, high heat capacity, which is very, very important. And another point, which is very important, is the high resistance to corrosion. Additionally, technological advantage, we can use electroplating, electrolysis from aqueous solution. And this is the fastest way to perform deposition. But we have also challenges. Copper diffuses into silicon and electromigration. In order to prevent diffusion, we use barrier, tantalum. This is copper, this is tantalum, this is silicon oxide. And this is silicon oxide, the copper, and tantalum. Tantalum is barrier because you see on this phase diagram, you see copper and tantalum don't like one another at all. Even in the molten conditions, they are separated into two different liquids. Another point is a very high density of tantalum. Tantalum is 16.6 density. So it prevents copper from diffusion into silicon oxide. Solve this, not easy. Electromigration. This is a very, very interesting phenomenon where electrons, a cloud of electrons, moves and takes and picks up ions in the metal ions in the metal and actually move metal from one place to another place that could result in the formation of voids within the metal interconnection. And this void is terrible. This is a failure of the device. Also here we found solution. Aluminum we use for low layers, copper mixed with aluminum. You see on the phase diagram, aluminum can be dissolved in copper, but aluminum doesn't like copper. See, at low temperature, at high temperature, yes, low temperature, no. And what's happened, aluminum diffuses on the grain boundaries and creates some coverage prevent it from made from aluminum that prevents penetration, movement of copper from one grain to another grain. Very good solution. Someone made very good PhD thesis, maybe not one. We continue to make transistors smaller, smaller, and smaller. And what happened also interconnection layers going in the perpendicular to this picture becomes smaller, but thickness of tantalum barrier remains the same because you should keep it in order to prevent diffusion. And the tantalum becomes very harmful because it takes volume, and it's not very, tantalum is not very good, conductor. And one of the way is to replace copper with cobalt. Advantages, first of all, cobalt doesn't need barrier. I will show you why. And another one, it becomes more conductive when metal lines are very thin. And also electroplating process is possible. And of course, challenges. First of all, cobalt, like iron, has very, very weak resistance from corrosion. And electroplating is also problematic. This is base metal. Its potential is minus. But it's possible to make electroplating. Why cobalt doesn't need a barrier? Because of this, you can see on this phase diagram a lot of compounds, intermediate, cobalt, silicon, cobalt salicide. And what's happened, cobalt diffuses into silicon oxide, interacts with silicon, and creates cobalt salicide. First of all, cobalt salicide have very high density, and they are very good, they have very good conductivity. Therefore, it's like a self-barrier. Of course, it's not like the process is not so trivial as I explained, but I'm talking about principles. The second, regarding conductivity, if we have a look on resistivity, of course, cobalt is much worse than copper, 3 times, 4 times. But there is another parameter which calls free pass, electron free pass. And in case of cobalt, free pass is about 40 nanometers. It means when the thickness of the metal layer becomes less than 40 nanometers, the resistance becomes very, very fast. Vlad, would you like to tell something? Okay, let's talk later. And what's happened with cobalt? Cobalt has about 10 nanometers. It means, and you see, because of free pass, cobalt for a very thin metal lines becomes more conductive. Let's move further. So we was talking about resistivity. Let's talk about C. because RC delay is resistance and capacitance. What to do with capacitance? Capacitance is a capacitance which appears between metal lines. What do we need? We need to reduce the electric permittivity. There is a ITRS, International Technology Roadmap for semiconductors, and they published the main parameters of semiconductors. It should be, or expected parameters, that allow to follow Moore's law. It's interesting. In 2000, they published, I pulled data and I built this graph. In 2000, the lowest K value was 3. And they published that in 2001, we will have 2 in a 7. In 2003, we will have 2. And in 2005, we will reach 1.3 K, the electric permittivity. In 2004, they said, okay, we're still on 3, but in 2005, we will definitely be here. In 2012, we will be here, and so on, so on. Where are we now? I can show you. This is evolution of dielectric materials. Silicon oxide crystalline, just for reference, never used in microelectronics. I just want to show that its dielectric permittivity is 4.5, and therefore amorphic phase is used. Amorphic phase shift from crystalline to amorphic phase allows to reduce the electric permittivity from 4.5 to 4. Great. Because we destroy the long order and we destroy the dipoles. The next step is fluorinated silica. People try to replace oxygen with fluorine, which is possible. Fluorine ionic radii is approximately the same as oxygen. We can replace it, but it has only one connection. So this is a way to destroy chains of silicon oxide and also reduce number of dipoles, and we got to the 3.5. The problem is that we cannot exceed a concentration of fluorine exceed 5%, and because this compound becomes decomposes. Okay, another component, another carbon-doped silica. Let's use methyl instead of fluorine. It also helps to destroy dipoles, destroy chains, and we can get to the 3. And if we create the same material, carbon-doped silica with porous, we can get 2.6. That's all. Guys, that's all. I don't see a lot of innovations here where we are like linked to silicon oxide. No one said, let's leave silicon oxide aside and try another material. This is, so I would say this is very, very problematic. RC delay is very problematic. How to solve problems with RC delay? To make a lot of layers, to make very, very difficult device. a lot of layers. You see, in this case, it's 16 layers. When we add layers, we can allow the larger thickness of metal lines, and we can increase the distance between metal lines. But the problem is that it's too easy for us. We are going too easy way because it's like psychological inertia. It's easy to make something complex. It's more easy to add layers instead of think and try to simplify it because it's very hard to make things simple. Let's have a look on the price. Terrible. Its cost. Terrible. You see how it increases. It increases. What's happened with the process? Number of steps increases, and you see cleaning steps increases dramatically. A number of cleaning steps. What does it mean? It means that we don't know. It means the previous operation creates defects, and we should wash these defects out. And instead of improve previous operation and reduce amount of defect, we add operation to wash it out. Very terrible. Let's remind that we are engineers. And the engineers can see everything, see as a system. And system is always components and functions. There are components that belong to system. There are components that out of system, but they are connected to the system through functions. So actually, we have component which impacts the another component. In this case, it's target. And this impact calls function. Function exists when any parameter is changes. If no changing in any parameter, no function. And what's happened? Today we think about component, and we should shift our paradigm and start think about function. Because when we think about component, we make system more and more complicated. When we think function, we psychologically think about simplification of the system. And simplification of the system is a real innovation. I recommend to use functional modeling. Our platform, PRIZ Guru, you can go and try it. It's a trial, it's free. We have number of different tools, and we have functional modeling, which is a system functional modeling. We have process functional modeling, and you can click learn more and learn how to use these tools. Just for example, I tried to create functional model of this layer, this fragment of the layer as a system. You can see components, and all the system can exist in order to provide current. And there is functions, useful functions. Red arrows is harmful functions. And platform calculates the main parameters of this functional model. And you see what's happened. It says a barrier, in our case, it's tandem barrier, is very functional, but also the most problematic. And this functional model is connected to 40 principles, and what came out is a gap instead of barrier. You know, we don't need to have very big gap. It could be gap of 100 nanometers. It's good enough to prevent diffusion. If we, I try to analyze the process again, the process of manufacturing of this layer. And this is a process flow. This is, let's say, the most trivial processing. In real life, it's much more complicated. But main operations that need to be taken to create this layer, you see 16 operations, 16 operations. And platform calculates calculated the parameters. And what's interesting, we have about 30% of productive operations. Productive operation is the only operations that add value to the product. We should keep in mind that providing all the rest of operation, providing corrective, metrology, all these operations is just wasting time and money. We still pay for this. We still do it because we don't know how to solve problems. We don't know how to innovate. We should switch our thinking again. We should think how to improve providing a productive operation because it adds value. And we should think how to eliminate providing corrective metrology operation. By the way, lithography is a providing operation. Lithography doesn't bring any value to the product. We don't need to spend money and time in the improvement of lithography. We should think how to eliminate it, or at least to make it easier. So this is what I wanted to tell you. I will send you the presentation. You can use these links, and please contact us when it is needed. We have some minutes. If you will, you can ask questions.
Yes, I have a question.
Yes, please.
So you say that you are replacing copper with cobalt. How are you depositing cobalt? Which technique is used? Sputtering or
Electroplating.
electroplating? Okay, and what was the thickness that you electroplate cobalt? Or is there any limitation like?
No, there is only one limitation. Let me show you something. The problem is not like this. The problem is different. Let me show you. I have another presentation. Yeah, I have another presentation about cobalt. You know, this is potential sequence of potential of standard electrodes. This is hydrogen 0, and here are all electropositive metals, and here electronegative metals. Generally, all these metals we can precipitate by electrolysis from aqueous solution. All these, no. We should decompose the hydrogen and after that precipitate. Therefore, aluminum or is produced, titanium produced from melt, and not from aqueous solution. But we know cobalt, nickel. We can deposit nickel on forks and knives, and also nickel. Nickel, its potential is here. What's happened? Moment. What's happened? There is a phenomenon that calls hydrogen overvoltage. Of course, when we have two electrodes, cobalt and anode, first of all, hydrogen comes to the cathode. Hydrogen ion picks up electron and converts into atom. Atom looks for spouse and converts into molecule. Molecule converts into the bubble, and bubble run out from the solution. All these processes take energy. And what happened? That potential of the cathode is changed. And the electrolysis of cobalt or nickel becomes viable. You can deposit. So therefore, from one side, you need to generate hydrogen bubbles, but you need to ensure that they all run out of the system, and this is the only way to create a cobalt layer. So I don't know regarding the dimensions. I just don't know. It's I'm just chemist. I'm interested in chemistry. I'm not in such number. I don't know if I answered your question.
Yes, thank you.
Yeah, this is the most problematic point. Yeah, guys.
Hello, Anatoly. I have a question. This is Dimitri.
Sure. Yes. Yeah.
Can you elaborate a little bit more on shifting to function from the component? Because the statement itself is engaging, but when you showed your functional map, there are plenty of functions. So how to shift to a function when you have plenty of functions?
Yeah, I see. This is the game. This is psychological way. You should stop thinking on how to deposit a metal line. You should think on how to conduct electricity.
Current.
You should current. Yes. You should stop thinking on how to deposit a layer of tantalum or tantalum nitride. You should, just a moment, you should think how to prevent diffusion. By the way, you should stop thinking how to multiply amount of transistors. Think on how to multiply functions of each transistor. By the way, if we have 10 billion transistors, do you believe they all operate in the same time? I don't believe it. I don't believe. But we should think on functions, because ideal system is a system that contains no components, only function. No system, but there is a function. My car is on the parking now, and I don't need my car. I need function when I need to move from one place to another. The same situation here. If we think about function, we can change component or system, or change system into more ideal situation.
Anatoly, Anatoly, hold on, because we have very limited amount of time. I'm going to step in because of who I am. That's just it. So the gentleman was specifically looking for the means, method, approach to get the alternative function that was going to give him the advantage. He was looking for the solution.
Yeah,
So,
I see.
Hold on. So let me finish, right? Because this is Intel's last innovation master speaking. Just so everybody else knows on this call. Correct? So as a matter of fact, what he's really asking for is what are all the other methods after you do the process functional modeling part that you've just demonstrated. Fantastic. But what he's looking for, if I'm interpreting correctly what he was asking, was what are the other methods that are going to help me to get to solution space? And that is all the other ones that you and I have talked offline about, Anatoly. But I think what I might suggest at this point is another presentation of what you've got here, where we demonstrate some of these other methods for the would-be attendees, so that they can see how to go from where we're at currently in the process functional model approach to what are potential solution spaces that can be pursued. I think that's what he's trying to get at. Correct me if I'm wrong, Dimitri.
Okay. Thank you, Richard. So what I mean, I'm crazy about functional modeling. Why? Because it makes you think about function. When you place the functional component, you thinking about function. If you have component without function, just terminate it. It doesn't make any sense to keep it.
Very good. Thank you. I've got answer from two sides for the same question.
Okay.
Good input
Okay.
for that. Yeah, very valuable.
Okay. Thank you. So, guys, I tried my best. Thank you very much for your attention. Yuli, would you like to tell something?
It's cool stuff. A lot of things to think about. Provocative as well.
As usual.
Oh yeah, that's what should be. Otherwise, yeah. Thank you very much, Anatoly. Thank you.
Thank you, guys. Many thanks. And meet another time.
Oh yeah.
Thank you, Anatoly. Thank you, everybody.
Thank you.
Thank you.
Bye-bye.
Thank
Bye.
you. Bye.